Moving on to example 2 in section 9.1. Suppose we have a box full of a mixture of red and white beans. We want to know the true proportion of red beans in the box. We gather a small scoop of beans and count out how many there are of each color. We count 30 red beans and 90 white beans. And to help you out, I have a little link here. So bit.ly, L-Y, / bean-box. I'll show you the link one more time. There, bit.ly / bean-box. And I have these pictures from right on my desk, right here where I'm making this video. And this is a box full of beans. And there's the white beans and the red beans. And then there's our scoop. You can see how little the scoop is in comparison to the box. Now I know what you're thinking. You're thinking, what in the world? Why do I care about beans in a box? You don't. The thing is that it's a metaphor. So suppose this is your group that you're looking at, and the red ones are all the ones that have a disease, or say are susceptible to cervical cancer, or say are the ones that would vote for Romney in the next election, or they're the ones that would oppose same-sex marriage, or whatever, right? Something like that. So the red beans are representing the people that you're interested in. Speaking of which, that's the first thing they say is, what is the box? Well, the box is the population, right? And just on a little side note, because when I taught this in class, some students had forgotten that the population size is equal to capital N. So it's the amount of beans in the whole box altogether. All right. Then the scoop of beans represents a sample. Okay. So what was our sample size? The total number of beans in our sample. And then what is its mathematical symbol? Well, that was N, which was 120, right? So we had 120 beans in our box, or excuse me, in our scoop. And I get that by taking 30 plus 90, which makes 120 total. Okay, so we had 120 beans. The total number of red beans was X, which was 30. So that's all we're interested in there is 30. Okay. And its mathematical symbol is X. Now the parameter we're trying to estimate is P, which is the population value, right? The population proportion, if you will, of all red beans in the box. So let me type that up. There you go. So it's the population proportion of red beans in the entire box. And of course, remember, it's a metaphor for a sample of a population. So you're thinking, what proportion of people are, I don't know, going to come down with anemia? What proportion of people are going to have breast cancer? What proportion of, et cetera, et cetera, et cetera. What is your best estimate for what the proportion of red beans in the box is? Well, you'd have to use your scoop, and your scoop tells you that it is P hat, which is X over N, which we know is 30 over 120, which is 0.25. So 0.25 is our P hat. That's our best guess. It's called the point estimate, right? The single best guess. Now, do we know the actual value of the population red beans? No, we do not. Right? Because that would require us to poll, if you will, the entire box, and we didn't do that. So no, we don't know the actual proportion because we did not sample the entire box. And no sample is perfect, right? Because of sampling error, right? Section 1.5, sampling error, right? All samples are going to be a little bit off, right? But we do think that P is close to P hat, right? We don't know how close, but we think so, right? That's the whole point of what we're doing. We're taking our point estimate and we're saying that we think that the population value is close to that point estimate. So we're going to build windows, if you will, intervals, ranges, right? From our sample statistics. So you're going to take your sample value of P hat and you're going to build from it in an interval, and you think that your unknown parameter P is somehow in there. So you're going to create a window of possible values for where you think that parameter is going to fall. That's the general gist of it. So the sample statistics we've used are P hat, which is X over N. So you take P hat and then you build an interval from it and you think P is going to fall in that interval. In section 9.2, we're going to take x bar, we're going to build an interval from x bar, and then we think that mu will fall in that interval, mu being the population mean, p being proportion. And then in section 9.3, we're going to take standard deviation or variance, the sample standard deviation, the sample variance, and we're going to build intervals, and then we think that the population standard deviation will fall in that interval or the population variance. That's the whole idea behind confidence intervals. You take your single statistic, your p hat, your x bar, your s squared, and you build a window, a range of values called an interval, and then you think that these population values fall in that interval, but you don't know for sure because you can never get everybody. All right, so let's look at the first formula for doing this, which is section 9.1's formula, which is right here. The confidence interval for population proportion P is this formula right there, right? So it's p hat plus or minus z alpha over 2 square root of p hat times 1 minus p hat over n. Now, p hat is called the point estimate, and we happen to know that it's the center of the interval, right? Center of interval for proportions. Well, that will not always be the case, but it is the case for proportions and for means. Then we also need these other three conditions, and these should be looking familiar to you because you saw them in section 8.2. Here are the notes from section 8.2, and you can see the central limit theorem for proportions, and lo and behold, look, random sample and independent. You need to have a large sample. Hey, n times p times 1 minus p is greater than or equal to 10. Then you have to have a big population. You have to have less than 5% of the population in your sample, which seems a little counterintuitive, but it's true. You don't want too big a sample. All right, so simple random sample, size n. We don't have what p is, so we use p hat. And this is to ensure that the distribution is approximately normal. And boy, do we need normal in a big way, right? So we always want to know or normally distributed. Let me put it that way. Be fancy about it. Then we want less than 5% of the population, which seems a little odd because you think, oh, you want the biggest sample possible. Well, not really. You want it to be less than 5% of your population size, and that's to ensure independence. Because what's happening is if you're going to call up people, let's say, you know, this box, let me find it again. There it is. So this box represents JC students, and the red ones are the ones that want to get rid of spring break, let's just say. And the administration's polling students wants to know if they want to get rid of spring break. What's going to happen is if you start calling more and more people, then somebody that doesn't want to get rid of spring break, one of the white ones, will start calling all their friends and saying, hey, don't you tell them to get rid of spring break. I love spring break. And they'll keep calling each other, and you'll lose independence. So you don't want more than 5%, because if you get more than 5%, you're going to end up losing your independence. You're going to end up going to be polling people that are all related to each other, that are all friends with each other, and you'll lose the fact that one person's opinion should not influence another person's opinion. And you will lose that if you get more than 5% of your population. Now, to be honest with you, this is the one we check the most often, right? So we check this one a lot. The other two, we don't check as often. We just kind of assume that we have them. In real life, that's not really a great assumption to make, but it's the assumption we make a lot of the times in our class. All right, now the margin of error, we've seen those words before, and we know that that's that distance from the edges to the center of an interval. That's what this back half of this formula is. So sometimes you'll have to use this formula, which is this big ugly thing, but sometimes you have to use the fact that it's half the width of the interval. Whichever is more convenient for you is the one you're going to use. So sometimes you'll use the big formula, sometimes you'll use half the width. If I were you, I'd use half the width if at all possible, because it's a lot easier to work with. All right, and then these are the calculator instructions, but we're not going to worry about those too much at this point. We'll come back to them in another video. And I'm going to stop right here because the next video is going to take a while, and I don't want to get us all bogged down in this one. So we've seen the formula, we've seen the conditions. Just as a little warning to you, you're going to need those conditions for, say, project, your project in the course. And then from there, we'll move on to finding what the z part is, because this formula has this z thing going on in there. So we're going to need to figure out what that is and how to find it before we can use the formula. So I'll see you here in the next video to do that.